Okay, so we are going to finish the lecture that we couldn't finish last time. I'm going to talk about the final element method and yeah. So before we talk about the finite element method, we're going to introduce the finite difference method, which addresses the problem of two-point boundary value problems. So consider the following example. You have a second-order differential equation where you have the coefficients associated to the differential equation, which are the polynomial p and q, subject to some boundary condition on some initial state A and final state B. The finite difference method proceeds by setting up a set of interior mesh points. So these are going to be at x1 is equal to the boundary condition plus h, then 2h, and then up to n minus 1h. So at each of these waypoints or mesh points, we're going to compute the differential equation, or we're going to see how we can compute that given finite differences. So the key idea is to replace the differential quantities by the central difference. So here we have a second order differential equation, so we will have a finite difference equation for the second order derivative and a central difference equation for the first order derivative. So if you look at the first order derivative, so this is simply what we saw in the last lecture, meaning the difference quotient between the value of the function at mesh point I plus 1 and the value of the function at point I minus 1. And we divide by the spacing between the 2 points. And so that gives us a finite difference approximation of the first order derivative. And for the second order derivative, we simply recursively apply that formula twice, and that's why we end up with these coefficients. So we have x plus 1 here, xi here, and xi minus 1 here. Okay, so evaluating the finite, the differential equation at these mesh points gives us a set of equations, linear equations, and we're going to solve that linear system by simply inverting the matrix where we compute the coefficients in a particular way, which I'm going to show here on this example. So now we've instantiated the coefficients of the differential equation by minus 4 here. So this is a constant, doesn't depend on x, on the independent variable. It's a constant coefficient here. This is actually a homogeneous differential equation of order 2. So we've seen how to analytically solve these differential equations. So here it's just an example where we have 2-point boundary conditions, and we are trying to find the solution on these grid points. So the finite difference method applies to all sorts of nonlinear differential equation, which would not be the case with the analytical solution. Okay, so when applying the finite difference method here, we are left with the following equations. So this is just applying the equation from the previous slide. And we have a resolution factor here, h of 1/4. So here, for the second order approximation term, we divided by 1 over h squared. So that ends up being 4 squared here. And yeah. So up. And this is, here we have 2h. So, is this, okay, well. So now we multiply the equation here by the resolution factor, and we simplify the equation, and we are left with this set of equations. So there are I equations corresponding to all the grid points, and the mesh points, sorry, and the mesh points are 1/4. So the boundary condition here was at 0, so 0 plus 1/4, 0 plus 2/4, and 0 plus 3/4. And so we are left with the following system of 3 linear equations that we can pack as a matrix and invert the matrix in order to solve the system of linear equations. And that gives us a solution for the dependent variable at each of the mesh points. So y1, y2, y3, where 1, 2, 3 corresponds to the index of the mesh point. So this can be compared to the analytical solution that we can get with the method that we saw last week. Okay, so what is then the finite element method? So the finite difference method is applied to a structured grid structure, or a structured grid where the approximation to the derivatives are computed by finite difference on the different dimensions of the grid. So the finite element method actually decomposes the domain using what are called elements, and these are unstructured and can have different shapes. So that's kind of the basic idea. It generalizes the finite difference method to these cases, and the solution is approximated by the linear combination of these finite dimensional elements. These are actually elements of a vector space. An example of basis functions for these vector spaces are going to be either global polynomials or piecewise polynomials or trigonometric polynomials, also Fourier basis functions and so on are also possible for the finite element method. When we talk about the finite element method, we usually actually imply that the basis functions chosen for solving the problem is a piecewise polynomial basis function for the vector space. So the question is, what is the polynomial? So a polynomial is a sum of mononomials, and the associated degree of the polynomial is how many mononomials are actually included in the polynomial. So if we have a polynomial of degree q here, we will have q mononomial associated with that polynomial here. And yeah. So we name PQAB the set of polynomials over an interval AB here, where q again is the order of the degree of the polynomial. And this is actually a vector space. So we saw how we can define a vector space of functions by having addition, which is element-wise addition between the two functions, and scalar multiplication, which is the scalar multiplication just of the elements of the functions themselves, of the image of the functions. Okay. So the space of polynomial is a vector space, and we have a familiar basis function for that vector space where we simply define the set of mononomials that are available. And then the coefficients will be the associated coordinates of that polynomial in that basis function, the basis. Another basis is the Lagrange basis, where here this is called a nodal basis, because we define the coefficient or the coordinates of the polynomial in that basis, which is called B2 here, by defining what is the value of the polynomial at a particular point here called xi. So let's see the vector space of Lagrange polynomial. So given that particular Lagrange basis B2, we can define a polynomial as the linear combination of the basis functions and the value that the polynomial takes at this particular nodal point. So Q will be the order, and when we write pi Q of L, it's actually the polynomial approximation of a particular function, L, using polynomials of degree Q. So we can then interpolate functions this way by simply having a few values of the function. So here we have 4 values which are used, and this is called pi 3. So counting from order 0 to order 3, pi 3 of L of x, given these 4 values that takes L, gives us an interpolating polynomial, which is this dotted line here, and the basis polynomial, the basis vectors of our vector space of Lagrange polynomials are going to be all these colored curves here. One thing to note is that in the Lagrange basis for the vector space of polynomials, we are very much subject to what is the order that we select when we interpolate a function. So here we see kind of a degenerate case where we are trying to interpolate the function, the gray function here, using a finite number of monomials or of basis vectors of our vector space. And what we find is that we have extremely high curvature between these 2 points, even though the curvature is very low here. So that might not be ideal for interpolating arbitrary functions there. So one solution for that problem is to use piecewise polynomials. So instead of interpolating the function globally, what we do is we compute locally little polynomials, and then we linearly combine them. So what we see here, these blue hat functions are the degree 1 Lagrange polynomials. So they are simply linear functions, and then we can define a coordinate associated to each of these basis vectors as the value that takes in the function at point x1, x2, x3, and x4, and so on. And this will give us the coordinate of that function approximated by these piecewise polynomial. So this is the idea of to increase accuracy and get rid of these degenerate cases is to use piecewise polynomials. But what's going to be important further is to actually have continuous functions, and so approximate our functions with piecewise polynomials that take on whose values are continuous. So it's a restriction of W to only continuous functions. Okay, so now we are equipped to understand the core of what the finite element method is, which is the Galerkin's method. And we're going to consider a very simple example. So this is something that we saw in the first lecture, which is the first order differential equation which relates the rate of change to the function value itself. We saw that there the solution to that differential equation is simply the exponential function itself. And here we, we are subject to an initial condition, simply here. So what we're going to do is we're going to search the space of possible functions for u restricted to the case where u can be expressed as a polynomial. So here, that's what we wrote down. So u is going to be the function which associates u0 plus a polynomial here, which is defined by the value taken at point. Well, no. So here we are simply using the basis function definition of a polynomial, the familiar one, where the coordinates associated to the vector, meaning the polynomial, are simply the coefficients associated to each order of the monomial. And so it's our vector space P here. And we define the residual error, meaning how accurate our solution is to solving the differential equation, by the following equation. So it says we have the left-hand side of the equation minus lambda times, well, so minus the right-hand side of the equation. And if that residual error is 0, then we match perfectly so we solve perfectly the differential equation. So Galerkin's method works in the following way. It consists of approximating the solution by finding a polynomial u whose residual error is orthogonal to v, and v being all the possible solutions for that differential equation. So we express this in the following way. We have the orthogonality condition expressed in the following way. So it's the residual error is orthogonal to the. So note that the residual error is actually a function of t. So the residual error is orthogonal to v, where v is any polynomial out of the space of polynomial v here. Actually, we are considering, so v is just arbitrary here. The space we're considering is actually P of Q. So the way we do this, the way we write the inner product, I remember that from the inner product of functions writes down this way. So we integrate the residual error times the function v over the interval 0, 1, and we equate that to 0, and that is for all the possible v functions. So that's just saying we want the we want the residual error to be orthogonal to all the possible function values that can be taken that solve the differential equation. All the possible v. And if we replace here our residual error by the actual definition of the residual error. And here we have our functional definition for our problem. A little bit of an intuition of why we write that down. Remember that when we say that a difference is a particular vector is orthogonal to all the possible vectors, What it means is that we are actually projecting the solution, so U, onto the space, the vector space of polynomials, of possible functions for that space here. So it's saying that we are looking for the closest solution to the differential equation on the vector space. Okay? Remember that if a particular vector, and so here our vector is actually U, is orthogonal to the basis vectors of the underlying vector space, it means that it's the closest point on that vector space. Okay, so coming back to our differential equation, or to our functional equation, we wrote down the inner product in the following way. And so here we have that we have expressed the integral in the following way. We replace the U by the polynomial with which we defined U here. So here, so here we derived U with respect to time. So this is U dot that we have here. And yeah, and so since this is a constant, if we take the derivative with respect to time, this will be kicked out. In the power here, multiplying t is lowered by 1. Okay? And then now, what we only have to show is that this equation holds for the basis vectors. So we replace v by the expression of each basis vector, and there are I of these basis vectors, which leads to I equations, or a system of linear equations. And we have multiplied by ti the two quantities inside the integral here, and then we moved them, and then we moved the part related to v, to u0 on the right-hand side, and that gives us our system of linear equations. So we can write down the system of linear equation. Also, we can compute the integral terms first. And so if we integrate t I plus, so j plus I minus 1 over the range 0, 1, we get that term here, and here we get that term here. And finally on the right-hand side we get that term here. Yeah, so this is a system of linear equation which has a unique solution. We can pack that into a matrix form, and we take u0 and lambda equal to 1, and the order of the polynomial equal to 3. And yeah, so that gives us that matrix, and we can solve it by inverting the matrix. This matrix is called the stiffness matrix. So now at that point, we have a similar system as the finite difference method. It's only that the coefficients are different in the sense that we computed them by computing what the integral of the polynomials would be. So we actually defined what the functions would be on the continuous range, whereas the finite difference method is more is more simple. It's more basic and kind of less accurate, actually. So accuracy in finite element method. The finite element method is the application of this Galerkin's method using a piecewise polynomial basis function. So this Galerkin's method can be used. It's just the idea of orthogonally projecting the solution onto the space, the vector space of possible functions. And this does not depend on how we decide to choose a basis function for a vector space. But the finite element method is actually the choice of having a piecewise polynomial basis function. And after computing the integral, the method solves to a linear system. The global polynomials lead to stiffness matrices that do not invert well in practice, so the one that we saw here. And so that's why we usually use these piecewise polynomial basis functions. And typically, in order to have better numerical precision, it's important to choose an orthogonal basis for the vector space. And yeah, when we use piecewise polynomial on a regular mesh, then the finite element method actually coincides with the finite difference method. So you're going to see this in the exercise lecture, where there are two implementation exercises, the one for the finite difference method and the one for the finite element method, and you will see that the solution to each of these exercises are very similar. Okay, so as a summary, the analytical solution to differential equations are very powerful when they are actually possible. We saw that explicit and implicit solutions are not always possible. The numerical solutions can then be used to approximate a solution, and the ordinary differential initial value problem can be well treated using our Runge-Kutta method that are powerful and provide a range of trade-off for accuracy and computation costs. We saw the finite element method that takes a variational approach to generalize the finite difference method and so on to the partial differential equation boundary value problem. And the key idea is to find a polynomial whose residual is orthogonal to the set of all possible functions. Okay, that's it.